All right, hi everybody. Today we're going to take a look at our day 2 lesson, which is on graphing systems of inequality. So yesterday we spent some time with writing systems of inequality. So now we're going to take a look at what that looks like on the graph and what the solutions appear to look like on the graph as well. We're going to use the Desmos graphing calculator as our technology today to do our graphing for us. So first I want to just review, when we graphed linear inequalities last week, like this, y is less than 1/2 x plus 2, we saw that we had a boundary line, and then one side of the boundary line was shaded, and the other side was not shaded. So in terms of, got a question down here, where are the solutions? The solutions for this inequality are in the shaded area, all along the shaded area, and keeping in mind this line extends in that same angle, and then the shading is going to always be below that line. If it's on a dashed boundary line here, those are not solutions, as we talked about last week. Okay, so in terms of where are the solutions, they're in the shaded area of this single inequality. What we're going to look at today is we're actually going to look at a system of inequalities, meaning we have two or more inequalities put together in the same system. So when we graph an inequality, we know that we're going to get a boundary line and then half of the graph shaded, one side of the boundary line. When we put two inequalities together, what we do is we graph both inequalities and they overlap. So we have this red boundary line that's dashed, and it appears to be shaded below the red line. We also happen to have this blue boundary line here, and everything is shaded below that as well, which it looks more like to the right, but technically it's below the line. So what we're looking for, where are the solutions to both of the inequalities? Well, this area over here in red, let me place a dot over there, make it a little bigger. All right, so this point right there, that is actually only a solution to the reddish inequality, whichever one that was. The dot up here is only a solution to the blue inequality because it's only shaded in the blue, but it's not shaded on the red side. So what we're looking for solutions to something like this is anything that's shaded where the two shadings overlap. So if I were to kind of draw this line, try that again. Kind of shade in all the way up to those boundary lines, but not crossing those two boundary lines and when they where they intersect. Okay, that would be our solution zone, or where our solutions are going to occur. All right, so it's not going to be in the unshaded area. It's not going to be in the area that's only shaded in blue, and it's not going to be in the area that's only shaded in red. The solutions are going to be where the blue and the red overlap. So that's where it's a little bit different with systems of equations, inequalities today. So I would like to go through an example with you real quick on our video today. And we are going to graph this system of inequalities and determine if these ordered pairs are solutions. And we're going to use Desmos to do that. So let me go ahead and open up our Desmos calculator. Oops. Let me go ahead and open up our Desmos calculator. Make this just a little bit smaller so we can see everything. Actually, you know what? We don't need to see it. We have everything in here already. I'm just hiding the view. So the first inequality, y is greater than or equal to -2/3 x plus 1, looks like this. We have our solid boundary line, so points on the solid boundary line are solutions to that inequality, as well as anything that's in the red shaded area. The other inequality, we have a dashed blue line, so points on the dashed line are not solutions, but anything in the blue shaded area is a solution to that inequality. What we want to look for is where do these two overlap when we show both of them. So we see that we have an area that's shaded only in red, so that's not going to have solutions to the entire system. We have an area that's shaded only in blue, that's not going to be any solutions to the system. We have an area that's not shaded at all, so that's definitely not a solution. What we have for the solutions are this area off to the right that is shaded in red and in blue. It's where those two areas overlap. That's where the solutions to the systems exist. Now we have two different boundary lines along this, this area that's shaded. We have a dash boundary line. So if anything happens to fall on that dash boundary line of the dark shaded area, it's not a solution. The other boundary line over here is actually solid. So if it happens to be on this boundary line, as long as it's along the darker shaded area, it's a solution. If it's on this solid line over here, it's still not a solution because these two areas aren't solutions. Okay, it's got to be on a solid boundary line of an area with solutions in it, where the shading is overlapped. Okay, so let's take a look at these ordered pairs and determine which of these are solutions. So let's start with 4, 3. We've got a green dot. There it is. Let's actually label that. And we can see that 4, 3 actually appears where the red and the blue overlaps. Maybe it's easier to show one at a time. It certainly is a solution to the red inequality, and it is also a solution to the blue inequality. Okay, so it is a solution to that system then. The next ordered pair is 1, 3, plotted in purple. So if we look one at a time, we can see that that ordered pair is a solution to the red inequality. And it is not a solution to the blue inequality because it's on the boundary line and the boundary line is dashed. So 1, 3 is not a solution. Let's look at the next one, -2, 4. And in this case, it's our black dot. We can see that it's a solution to the red inequality, but it is not a solution to the blue inequality. So that is not a solution to the whole system. 6, -3 is down here. Oops, forgot to label again. 6, -3 is right on the solid boundary line, and it happens to be on the boundary of the area that has all of our solutions. So because it's on the solid boundary line, right along the area that has the solutions, that actually also is a solution. So notice the difference between the purple dot, which was not a solution because it's on a dashed line, and the red dot that is a solution because it's on the solid boundary line. -1, -5 is a solution to the blue inequality because it's in the blue shaded area. But notice it's not in the red shaded area. So it's not a solution to all of the inequalities in that system. So that is not a solution. And last we have -6, 1, which is over here in the area that's not shaded by either one. It's not shaded in red or blue. So that's really the one where it wasn't a solution to either inequality. So we can see here it's not a solution to the red inequality, and definitely not a solution to the blue inequality either because it's on the opposite side of the shaded area. So the only ordered pairs that were solutions here was 4, 3 because that was in the area shaded in red and blue, and then 6, -3 because that was shaded, excuse me, it was on the solid boundary line. It was a solution to both inequalities. So 4, 3, 6, -3 are the only two that are solutions. All right, our day 3 lesson is on finding the feasible region and the vertices of a system of inequalities. Now, if you haven't gone through and watched the day 2 video, I would recommend doing that first because that's going to describe how we graph a system of inequalities and what that looks like. So here are the definitions for today. A feasible region is the set of possible solutions in a linear programming problem. In other words, it's the shaded area and any solid boundary lines along that shaded area. Now, a vertex, or vertices, if we're talking about more than one vertex, is a corner of a feasible region where two or more boundaries meet. So the feasible region is the solution area, so all the different shaded areas that overlap, but also the solid boundary lines along that shaded area. And then the vertices are those corners. So let's take a look at a visual for you to get a better picture of this. So let's say I've got my boundary lines here on some type of problem, and I see that the overlapping shaded area is inside the middle of this quadrilateral here. So you can see it's shaded in gray. that whole area is what we call the feasible region, like feasible area. That's where all the solutions are feasible or possible for this linear programming problem. Now, the vertices are the corners, okay? Now, it's not all the corners that you see on the graph everywhere. It's only the corners along this feasible region. So when we shade just inside this shape, we see that there are 4 corners, and those corners have coordinates, the x and y coordinates that we can use to apply a name. Now, these vertices are important because these are the x and y pairs that we're going to use next week with our objective function. So remember, with our application problems, there's always a reason why we're looking for a certain combination of x and y. It might be to maximize profit, or it might be to minimize fat content, or but for the most part, you're trying to either find a maximum value or a minimum value. And those maximum and minimum overall values aren't going to come from combinations inside the feasible region. It's always going to come from one of the corners or vertices of this feasible region instead. So that's why we want to focus on finding the vertices of the feasible region. Let's actually take a moment to do a problem like this together. So this doesn't have any context to it. There's no application, but this is just a system of inequalities listed here. We're going to find the vertices of the feasible region. So to do that, we want to start by graphing the system. So we're going to use Desmos to do that. We're going to identify the feasible region based on which shaded areas overlap. And then we're going to identify the vertices of that feasible region. So let's get Desmos up here. And we're going to have to start by typing in our inequalities. So y is less than or equal to 1/2 x plus 3. We have 2x minus y is less than 6. And 2x plus 3y is greater than -6. Now let me just double check and make sure that I typed that in correctly. Okay, looks good to me. Now let's make it full screen. Okay, so if we take these and go one at a time, I don't really like to have the color black on there. It's just too dark. Let's go orange for this one, because I think the others were red and blue. Yep. All right, so for this first one, the orange one, the feasible region just of that one inequality is down below. It's where our solutions are, below that boundary line. When we include the second one in red, we see it's to the upper left-hand side of that red. So what area do these two have in common? It's down here, the one that's shaded darkest in red and orange. So as of right now, that's where our solutions would be. But we have a third inequality that also says it has to be above this boundary line. So what area is shaded or overlapped by all three? It's in the middle of this triangle here. Okay, so this would be the feasible region, anything inside the triangle formed by these three boundary lines. All right, so here's my boundary lines. What I need to do is shade inside of there. So I'm going to actually use a highlighter and try to shade that as best I can. I apologize if I go outside of the boundary lines. Try to stay inside as much as possible. There we go. All right, so that's our feasible region. Notice it's anything on the inside where it's shaded, and it's also along this edge, along this side, because that's the solid boundary line. Those are solutions. Anything on this dash boundary line is not a solution. This dash boundary line is not a solution. Okay, so what we're looking for next is we are looking for the vertices. So we want to know what are the coordinates of these three corners that we have along our triangle. Sorry. One, two, three. Okay, so to find that, we're going to go back to Desmos. And remember, in Desmos, you can literally just click on it to see what it looks like. So if you click on any one of these boundary lines, it's kind of going to change the shading. but it also makes those intersections appear. Notice I have a dot here, but that's not the intersection of my boundary line, so I don't really care about that. That's just my x-intercept of that line. And I got one more corner over here. All right, so those are my vertices. So I have 6, 6. I'll label that up here, 6, 6. Down here, I believe that was 1.5, -3. And I saved that third one for last because that's the hardest one. It's got all these digits. So -4.286. And we don't want to round on this. We want to give exact values, 0.857. All right, so that, of course, is that vertex. All right, so we have 3 different vertices, and we have found them using graphing technology. So that's just a basic example. And again, next week when we talk about objective functions, the maximum or minimum value that we're looking for in a linear programming problem will always happen at one of those 3 vertices. So those are the important ones. So on Monday, we talked about these application problems, and one problem we did was on Brantley's Bakery, having these constraints that we wrote together, these inequalities. So we're going to graph the system of inequalities, and then we're going to use that to sketch, just like we will on the assignment for today. So if you haven't already, you maybe want to pull up the assignment, the day 3 assignment, and then we'll go through this together. All right, to try to save a little time, I have this pre-typed in here. And we're looking for where these 4 sections or areas overlap, finding that feasible region. So kind of going one at a time, I can keep track of what area is the feasible region. And if I zoom in on this, I can see that it's going to be in between here. Okay, so I don't really care about this dot up here because that's not below this red line. So it's got to be below the red line, below the blue line, above the, I guess I'm not sure what color that line is, purple maybe, and then to the right of the green line. Okay, so it's inside this quadrilateral shape. All right, so I'm going to go back to Desmos, and we are going, excuse me, back to our lesson, and we are going to sketch by plotting our points first. Okay, so when you're in Cami, change the size of your dot to maybe like a number 6 or a number 8. And then I want to put a dot at 0, 9, 0, 0, 6, 0. So 0, 9, 0, 0, 6, 0. And then that last one was at 1, 8.333. So 1 and then 8.333 would be just a little bit above the 8, right in there. In Cami, you have that straight line tool as well. So I would encourage you to use that rather than trying to freehand it. And all of my lines were solid, so I don't have to worry about changing that to dashed lines. There we go. And then we also fill it in. Okay, so you can just grab your pen, or in this case, I like using my highlighter. It just colors a little bit faster when it works. There we go. All right, then the last thing that we need to do is just identify what those coordinates were by listing your vertices. So we had 6, 0, 0, 0, 0, 9, and if I remember right, this was 1, 8.3 repeating on that one. All right, so that is all we need to do for the application problem. We've got the inequalities already listed. You just graph those in Desmos. we find that feasible region, click on the vertices, and then we're just transferring that over to your assignment. So just like I did, I would encourage you to plot the ordered pairs first, plot those vertices, then connect them with your lines, color it in, and make sure to list each of the vertices on that.